Picture this. You're driving at a breakneck speed of 100 kilometers per hour nonstop. It would still take you about 287 million years to cross the Milky Way. That's how incredibly vast our galaxy is. The Milky Way, our home galaxy, is a sprawling spiral cosmos that stretches about 100,000 light-years across. To put that into perspective, if a light-year were condensed to the length of a meter stick, the Milky Way would span the length of 100,000 of them, lined up end to end. And within this immense expanse, there are an estimated 100 billion stars, each with their own unique cosmic story. That's more stars than there are grains of sand on all the beaches on Earth. From red giants nearing the end of their stellar life cycles to white dwarfs cooling down after their fiery past, the Milky Way is a bustling metropolis of stellar citizens. Moreover, our galaxy isn't just wide, it's also thick. It's about 1,000 light-years thick, which means that if you were to travel from one side of the Milky Way to the other, it would take you 1,000 years to travel at the speed of light. And that's just the average thickness. In the middle, where the galactic bulge is, it's even thicker. But despite its size, when we gaze up at the night sky, we're only able to see a fraction of the Milky Way's grandeur. The majority of its stars, gas, and dust are too far away, too dim or obscured by interstellar matter. Yet even the tiny fraction we do see is enough to fill our night sky with countless twinkling stars. So the next time you look up at the night sky, remember that you're viewing just a tiny fraction of our colossal galaxy. Each star is a distant sun, potentially with its own family of planets. Each point of light is a testament to the vastness of the cosmos. Each twinkle is a reminder of our place in this grand cosmic tapestry. Imagine being in a place so quiet that you can hear your heartbeat. That's space for you, an absolute silence. It's an eerie, all-encompassing quietness that is not just about the absence of noise, but also a reflection of the profound emptiness that characterizes the vast expanses of the universe. Why is space so silent, you ask? Well, the answer lies in the very nature of sound itself. Sound, as we know it, needs a medium to travel through. It's essentially a wave of pressure that moves through substances like air, water, or solid objects. When we speak, the vibrations of our vocal cords create these pressure waves in the air around us. These waves then reach our ears, causing our eardrums to vibrate, and voila, we hear sound. In space, however, there's no air or water or any other material medium that sound waves can travel through. It's a vacuum, meaning it's almost empty of matter. So in the absence of a medium, these pressure waves cannot be created and hence cannot propagate. This is why space is silent. Now, this doesn't mean that communication is impossible in space. Astronauts, for instance, communicate with each other and with mission control on Earth using radio waves. Unlike sound waves, radio waves don't need a medium to travel through. They're electromagnetic waves, much like light waves, and can move freely in the vacuum of space. These waves travel at the speed of light, allowing for near-instantaneous communication over vast distances. However, it's important to remember that while radio waves can carry voices and other sounds from Earth into space and vice versa, these sounds can't be heard directly in the vacuum of space. They need to be picked up by a receiver and converted back into sound waves that our ears can interpret. In the vast expanse of space, no one can hear you scream, sing, or even whisper. Think about this. If you could stand on a scale in space, it would show 0. Yes, you'd be weightless. Imagine the sensation of floating around, unbound by the shackles of gravity that keep us grounded here on Earth. This isn't the stuff of science fiction, but a reality for astronauts aboard the International Space Station, or ISS. You see, in space, there's a phenomenon aptly named microgravity. It's not that gravity doesn't exist in space, quite the contrary. It's just that it's incredibly tiny. So small that it's as if you're perpetually falling but never hitting the ground. It's a bit like being on a never-ending roller coaster ride, minus the stomach-churning drops. This microgravity environment is what gives astronauts that sensation of weightlessness. It's not just about floating around, though. This weightlessness affects how their bodies function. From their bones and muscles to their cardiovascular system, everything operates differently when they're off the ground. In the absence of gravity, muscles and bones don't need to work as hard to support the body, which sounds great until you realize that muscles and bones can weaken over time. That's why astronauts need to exercise for about 2 hours each day to maintain their muscle mass and bone density. Similarly, without the pull of gravity, the heart doesn't need to pump blood as hard. Over time, this can lead to a decrease in the size of the heart. So it's not all fun and games being weightless in space. There's a lot of work that goes into staying healthy. But let's get back to the fun part, the weightlessness. Picture yourself doing somersaults in midair, sleeping vertically, or eating floating food particles. It's a whole new world up there. A world where the mundane becomes extraordinary and where the ordinary rules of life on Earth are turned on their head. So, in space, you can finally ditch that diet and still weigh nothing at all. Ever thought about the universe's speed limit? It's the speed of light, clocking in at an astounding 299,792 kilometers per second. Now imagine you're in a cosmic race and the speed of light is the fastest you can go. It's like the ultimate speed limit, a cosmic law that nothing in the universe can break. This speed limit isn't just for physical objects, but also for any information that travels through space. So, why does the universe have a speed limit? Well, it's all thanks to our friend Albert Einstein. In his theory of relativity, Einstein proposed that the speed of light in a vacuum is the same, no matter the observer's speed or direction. This idea, as simple as it sounds, has profound implications, but how does this cosmic speed limit affect our perception of the universe? Let's consider our closest star, Proxima Centauri, which is roughly 4 light-years away. This means that the light we see from Proxima Centauri today actually left the star about 4 years ago. In other words, we're seeing the star as it was 4 years in the past. This concept extends to all celestial bodies. The farther away a star is, the farther back in time we're looking when we observe it. For instance, when we look at a galaxy that's 1 billion light-years away, we see it as it was 1 billion years ago. So the cosmic speed limit doesn't just limit how fast we can travel or send information. It also shapes our perception of the universe and time itself. It's a humbling thought, isn't it? Even with all our technological advances, we're bound by the laws of the universe. We're cosmic time travelers, peering into the past every time we look up at the night sky. Remember, when you gaze at the stars, you're essentially looking back in time. Contrary to what you might believe, time doesn't tick the same everywhere. In space, it warps. Imagine you're a cosmic traveler journeying through the vast expanse of the universe. You're not just moving through space, but also through time. This is all thanks to Einstein's theory of relativity, which tells us that time and space are intricately linked in what we call the SpaceTime Fabric. Now let's delve a bit deeper. The theory of relativity is composed of 2 parts. The first is special relativity, which states that the laws of physics are the same for all observers, regardless of their speed or direction. Seems straightforward, right? But here's the kicker. The speed of light is constant for all observers, no matter how fast they're moving. This leads to some mind-boggling outcomes, one of which is time dilation. Time dilation is the idea that time passes at different rates in different gravitational fields. The stronger the gravity, the slower time passes. This is known as gravitational time dilation, but gravity isn't the only thing warping time. Velocity, or the speed at which something is moving, also affects how time is experienced. This brings us to the concept of velocity time dilation. According to this, time slows down as you approach the speed of light. The faster you move, the slower your time ticks relative to someone who is stationary. Now imagine being near a black hole which has incredibly strong gravity. Time there would crawl to a near standstill compared to time on Earth. So if you're planning a trip near a black hole, your watch might just tick slower than those on Earth. But remember, this isn't just theoretical physics. GPS satellites have to adjust for time dilation effects to provide accurate positioning data. Isn't it incredible how our understanding of the universe translates into practical applications? So, as we journey through the cosmos, we're not just exploring space, but also the very nature of time itself. Isn't that just mind-blowing?